share my right now is recording?
Yeah.
It's recording. Today we will solve some question covering the example which is from chapter 1 to 5. I have prepared the 8 questions to solve it. I hope they will help you. Let's begin with the first question. First question is related to vacuum pressure and gauge pressure. Let's read the first question. The vacuum pressure of the gas contains 10 kilopascal at location where the atmospheric pressure is 100.325 kilopascal. If the container is located on a mountain at an altitude of 100,000 meters where the atmospheric pressure is 85.6 kilopascal, determine the absolute pressure and gas pressure of the gas. As we know that P vacuum pressure is related to P atmosphere and P absolute pressure. The absolute pressure is the actual pressure that doesn't change according to place. So we know that at the kind of sea level, the atmospheric pressure is 101.325 minus P absolute. In the question, P vacuum pressure is given to us, 10 kilopascal also, and then the absolute pressure will be 91.325 kilopascal. The question is asking us, find the absolute pressure. Absolute pressure will be same at that location and that location, because the absolute pressure is the actual pressure, it doesn't change with place. We know the absolute pressure, and we know that Gauss pressure is related to atmospheric pressure and absolute pressure. The Gauss pressure, we know the formula for the Gauss pressure. Absolute is equal to the gauge pressure plus atmosphere. At the location, the altitude is 1400 meters. The atmospheric pressure is 85.6 kilopascal. Gauge pressure will be 6. We know the atmospheric absolute pressure of gas. And then gauge pressure will be 5. Anyone has any questions?
So even where you imply that absolute pressure doesn't change, it's all the same as on the top of
Because gas is inside the container and has some specific pressure. That pressure is absolute pressure. This is the actual pressure. Yeah. Gas phase doesn't change. After calculating the absolute pressure at that level, we can, because the vacuum pressure is given to us, we know the atmospheric pressure at that level, we find absolute pressure of gas. And when the gas container is moved to mountain, the absolute pressure will be the same. And then, but the atmospheric pressure is the change, therefore you will reach different value from the gauge. clear? Or anyone have any questions? Do I have to move on or?
In the question, is that the vacuum pressure of a vacuum containing 10 kilopascals, that means the absolute pressure of 10, or
No, vacuum pressure is.
the vacuum pressure, that's gauge?
Yes,
Okay.
yes.
The vacuum pressure on
Yes.
gauge.
Yeah, vacuum pressure is under the atmospheric pressure. We know that formula, right? For the vacuum pressure. At that level, the atmospheric pressure is that one. Down the 1.2, right? So we can find the absolute pressure of the gas. That pressure does not depend on the rotation. The second question is related to the temperature scale. During the heating process, temperature of the system rises by 1 express rise in Kelvin Fahrenheit and and you know that there are some temperature relation between centigrade, Kelvin, Fahrenheit, and Rankine. It's very complicated. Question says that during the heating process, the temperature of system rises by 10 centigrade. That means that delta T in centigrade is 10. Let's suppose that before the heating, the system temperature is T. That we don't know. The initial temperature in Kelvin will be plus after heating the temperature, let's say the final temperature, in Kelvin will be 1 plus 10 plus therefore delta T in Kelvin will be the same, like centigrade. Final minus function. And it will be the difference between 10. In Kelvin scale. If we look at the Rankine scale, we know that relationship. Delta T Rankine will be delta H 1.8 delta T delta. And therefore, we know that we calculated the delta T Kelvin, it was 10. Therefore, the Rankine scale, the change of temperature in the Rankine scale, it will be 80. For the Fahrenheit, we know the same relationship between centigrade and Fahrenheit. Delta T Fahrenheit is also going to be 15. I'm not able to write what the units. This is the problem. We use the temperature scale relationship, and after finding the Kelvin, we said that we know that this relationship, if the Kelvin temperature is increased 10, the Rankine temperature will be increased too. But there is a converting factor here. temperature will increase 18. And also we know that the relationship between centigrade and Fahrenheit, that is the constant, doesn't affect the temperature increase. It will be better if temperature will increase 10, that will increase 1.8 times temperature. Is that clear or?
There's a difference in temperature of 10 Celsius,
Mhm.
and then you're inserting that 10 Celsius in the last equation with TF,
Delta T, yes.
delta T,
Yes.
F.
Here.
Okay, so it's 1.8 times 10 plus 32.
Mhm. Let's do it like this, if you want to. Because this part is clear, right? We can say that this is the first temperature is 10. And we can put the final temperature 10 plus, first temperature is T, and the final temperature is T plus 10. Because this is the constant part, doesn't affect the calculation. They will cancel each other. It will be 1.8 times 10. If you want, I can do the same thing. Like this. In centigrade is T, you don't know. The final one, T final. If you insert a volts temperature in this equation, the initial in Fahrenheit will be 1.8 T plus 32. In Fahrenheit will be 1.8 times 10 to the T plus T plus 10 plus 32. Raised with delta T in Fahrenheit will be final minus initial. Final temperature is 18, 1.8 times 18 plus input plus 32 minus initial temperature plus 32. Using brackets for the night. Minus 32. 32 will cancel each other, and this is also minus. And the delta T will be 18. önemli var mı? Dünya basın. The third question is related to monometric. It's a bit complex. Probably you will have a monometric question in your exam. Please interrupt me if you have any questions when I solve the question. It would be better. So I'm not sure if you're aware of there is a bridge here that you will illustrate. You have a reduced here, let's say A, and another reduced here, let's say B. That height is 2 meters, and that includes specific gravity of that object is 1. Specific gravity of A is 0.8, and that height 0.5 meters. A and B is immiscible. A and B are immiscible liquids. Monometric view. Another gas, let's say nail, and that container is connected to manometer and open the atmosphere. The atmospheric pressure is 101.3 kilopascal. And that high difference is 50 centimeters. And that high difference is 150 meters. Question is asking to determine the gauge pressure of nitrogen gas. That pressure that you add nitrogen. As a main gas. And we know the specific gravity of liquid, let's say the C, is 13.6. Anyone has any suggestions? We start with questions, so the question. Neon pressure? Yes, yes, yes. Oh, very good. Yes. If you know that pressure, and we can calculate the pressure, right? Because we know the atmospheric pressure, and it's certain that the liquid is rise up in this way. It means that the pressure of neon is lower than the pressure of atmospheric pressure, right? We can write that most pressure balances. And we know that the liquid pressure does not change with horizontally, and we can say that at this point we can establish the pressure balance because the fluid pressure does not change with horizontally. That pressure at that point must equal to the pressure at that point, right? And then we can say that the atmosphere is going to equal to neon plus rho C times G times HC. How can we calculate rho G? The specific gravity is given to you. You know that formula, right? Rho G is equal to specific gravity C times rho water at 4 centigrade. And specific gravity C is given to us 13.6 times. We know that raw water, density of water is 1,000 kilogram per meter cube. Therefore, rho C is going to be 30,600 and then I know the P atmosphere pressure. I calculate times G is gravitational acceleration is constant meter per second square times HC. It's going to be 0.05 meter. That unit is going to be Pascal. That's why I put the Pascal unit here, not the kilopascal. If I put the kilopascal here, your calculation will be wrong. Because after the multiplication, you will get Pascal units, not the kilopascal. That is going to be Pascal, and then it's going to be let's say here is point 1 and point 2. We created the pressure balance here and calculated neon pressure. The gas apply the pressure to everywhere the same. Therefore, that pressure, that gas applies the same pressure here and applies the same pressure here. And we can use the same approach. We can create another pressure balance. And we can say that the fluid pressure at that point, let's say point 3, it's going to be equal to, at the same level, this is 2 meter. There is some difference here. Let's say point 4. They must be equal to each other. Yeah. Yeah.
Right there in the first line, we have multiplied by 0.35. Equals
0.05?
50 centimeters.
Yes.
0.5.
Why 2.5? 0.5. This is right? No. This is the decimeter, right? Centimeter, decimeter, and meter. This is the scale, right? Meter, decimeter, centimeter, and millimeter, right? It's asking to 50 centimeter. It will, oh, sorry, here. This is the, oh, sorry, that will be 5. Sorry. Yeah, let's do the same pressure balance for this part. Can I erase this? Until that point, do you have any question?
The P18 kilopascal,
Yeah,
and here we in Pascal,
I
right?
use Pascal. Because that, after that multiplication, you only do the Pascal. If you insert kilopascal, that will be wrong. And we got the result that we expect because if you observe that the neon pressure is lower than the atmosphere because that liquid rise up in this one.
So that's the answer.
Yeah, for neon pressure.
And why should it be in Pascal and not kilopascal?
Well, because when you multiply this one, this is kilogram.
Oh, I get it.
You have it? That's when it will be the Pascal. is going to be here. So the pressure at point 4 here. Same relationship that we used here. The pressure at point 3 here is going to be pressure nitrogen plus rho A times G times H. Pressure at point 4 will be pressure N plus rho B, because there is some liquid here, liquid of B, times G times HB. HB is the depth difference, because we know that this is 2 meter, depth R is 2.3 meter, H will be the depth difference, because we are establishing our pressure balance at that point. Is it clear to everyone? So, rho B is going to be specific gravity B times rho water is going to be 1 times 10,000 to per meter cube, and that's going to be 1,000 per meter. Rho A is going to be specifically to go so specifically to 0.8 times 1,000.
H2 is 2.3 minus 2.
Yeah, because the all height of the two 2.3 meter. And we established pressure balance at that point. At that point, the height is 2 meters. So the pressure balance, we are dealing with that pressure and that pressure. Yeah?
Right.
Yeah,
How do you know this is the gravity of,
still,
plus 1?
yes, one.
So,
Sorry about the drawing because it's not as easy to do.
so only you get 1.1 there.
Here, this is the one.
Yeah.
This is the,
Oh, time is also minus.
yes.
Instead of using the bottom baseline
Mhm.
the precision of height, we make the baseline
Here, going to be the same. Because that pressure is the same. You will insert extra calculation. It's not necessary. It will be look, it will be rho B times G H. The H is 2, and you need to insert the T also, same thing. Because you are picking that one point, right? It's going to be same. Rho B, G, and 2. So they will cancel each other. Yeah, it's important. Which are this. But you know that the fluid pressure does not change the horizontal, it's changing it vertical.
Yeah.
So at the same level, the pressure must be equal. Yeah.
So, for example, let's say that the B on the left side is at 2 meters, and then on the other side is at 2 meters. Then there's 0, right?
Yeah, only the have narrow pressure, right? Yes. But there is a difference. Fluid pressure. Yes.
So now we substitute the equation.
Yes. Can I erase all of that? I will substitute all of them in this equation. But I should be careful about the units. If I put wrong units, the calculation will be wrong. So I will pick the Pascal that you obtained here. 4.2 Pascal at now plus calculate 1,000 meter cube times specific gravity 9.51 meter per second square times 0.3 meter is going to be nitrogen plus the only unknown in nitrogen. The nitrogen is going to be question asked us determine the gauge pressure of nitrogen. Right? We know that P absolute is going to be P gauge plus P atmosphere. We found the nitrogen pressure, but is it the absolute pressure or gauge pressure? That's the absolute pressure. This is the absolute pressure. We know that this relationship, right? The pressure that we calculated always the absolute pressure. The gauge that you are reading shows you related to atmosphere. Therefore, we use that pressure. But the pressure that you calculated from the hydrostatic pressure and from the manometer, it's going to be absolute. Do you have any question? Or I should know. Is it very clear? More and this question is full conversion problem. Everybody knows ideal gas load, right? The question is asking convert the equation to 1. Let me add this equation. That is going to be P gauge in terms of atmosphere. Volume in terms of liter and number of mole in terms of mole and temperature is Kelvin. Is gauge is connected to the container. Is for atmosphere that you are reading on the gauge. This is calculate the amount of gaze that is more and the mass GSI G represent the gauge pressure, GSI A represent oxygen. GSI is the unit of pressure. Or second interest.
So how do you know?
In this case, this is the absolute, right? Can I read this text? Yeah. The parameters. Absolutes. Normally, with that formula, we use PSI. But we are looking for, let's say, P prime absolutes in terms of atmosphere. So you have to use some converting factor, right? To obtain P absolute in terms of atmosphere. You know that atmosphere is going to be equal to 14.6 PSI. Absolute in terms of atmosphere. Okay. The absolutes is going to be the prime absolutes in atmosphere times 14.696. But the question asking us the relating to gauge pressure, so we know that the prime absolute in terms of atmosphere is equal to P gauge in atmosphere plus atmospheric pressure in terms of atmosphere. When we insert that equation to here, it's going to be the absolute PSI G gauge atmosphere plus 1 times 14.696. We described our atmospheric pressure in terms of our absolute pressure in terms of gauge pressure and also in terms of atmospheric pressure. Is that clear? Device the atmospheric pressure here. Atmospheric pressure is standard pressure is 1.
Absolute gauge, right?
Yes, gauge pressure, not absolute. We will insert that equation in our GVT and NRT equation. We will insert whatever we read from the gauge, and that relationship will give us PCI. But we will use atmospheric pressure that we obtained from the gauge.
Okay.
Does it make sense?
You're going to use the gauge pressure in that equation.
Yeah, I understand.
But in PSI.
Here,
Yeah, in that equation.
yeah.
So, instead of converting the PSI to the atmosphere, divided into what?
I'm looking for atmospheric pressure, right? Because the person asked us the car pressure, find the pressure, gauge pressure in terms of atmosphere. So I have to change PSI to atmosphere first. But that pressure will be absolute pressure. So that's the equation only you can insert the absolute pressure. Yeah, and also you know that absolute pressure is related to the gauge pressure that you will read from the glass. And we know the atmospheric pressure is the standard pressure. We can insert that and we can find absolute pressure of gas. And I said, plug it here, it's going to give us the absolute pressure of the gas. We will do the same thing for the volume. Our volume is in terms of heat, and we need to find some conversion factor to obtain volume in terms of liquids. We know that here so yeah.
So is that, you know, like you have P prime for the,
How this is equal?
well,
No, we just said that people. Oh, okay. You can put, I mean, it's represent a different one. But this is not the plan, sorry. This is the,
It has to be ATM, right? Is it right? It has to be atmospheric pressure.
no. This is the atmospheric, this is the atmospheric one.
Yeah.
This is the absolute. I insert this equation to here, so this is the PSL,
Okay.
right? This equation is the final one. This is the only, this part. Because we have that multiplication here also. Later, it's going to be new volt. That's why and later. This is the relationship of volt. Important mode and temperature. Real number is given in terms of pounds mode. But we are looking for mole number in terms of mole. We know that 1 pound more is going to equal 453.593 gram more. Then pound more and prime in terms of mole. So no temperature relationship between Kelvin and Rankine. Rankine is going to be 1.8 Kelvin. So we inserted our converting factor to find the variables in terms of Ricard mole numbers, Kelvin, and liter. Then we insert all variables, that equation. We will get pH in terms of atmosphere plus 1. Times 14.6. plus or so it's going to be in terms of ranking. This is our rank in terms of pounds. This is our volume. And this is our pressure in terms of I just inserted all of them to designation of state. By the new calculations here, you will get simpler. That we normally use in assignment system, right? This is the atmosphere, this is liter, this is ideal gas constant, this is mole, this is Kelvin. Normally we use this equation. Anyone has any questions? Yes, this is the question that we will use in part B. Part B is asking to us 20 more percent carbon dioxide and 80 more percent carbon monoxide gas, which is stored in a container with 100 liter. And the temperature in terms of Kelvin is giving us 302. And the gauge pressure is 44 atmosphere. It's asking us to calculate the total amount of gas, M. So it's going to be, and the mass of carbon dioxide in the quantity. So we put plus 1 times 172 and prime and then the more times and one number is going to be and prime. Total mole. That gas which is containing carbon monoxide and carbon dioxide, the mole fractions are given to us. If this is the total number of gas, we can find that and carbon dioxide is going to be X carbon dioxide, the mole fraction of carbon dioxide times and total. If you will use that and total here, then and carbon dioxide is going to be mole times 0.2, because this is the mole fraction of carbon dioxide, and that value is 8.06 mole carbon dioxide. The gas mixture contains 38.246 mole carbon dioxide. The mass of carbon dioxide, you know that 9 numbers is going to be mass carbon dioxide or molecular weight of carbon dioxide. This is 38.246 mass carbon dioxide over 0.032. Moles, we cancel each other because this is also unit mole. The mass carbon dioxide is going to be 1.253 kilograms. Sorry about my writing, it's not easy to write. Correct? You need more number? Oh, this is kilogram. 1.253 kilogram.
I don't understand what you need to get in. Yeah. What was it? N prime?
Yeah, and prime in terms of mole. We define all variables in terms of required scale, atmosphere, liter, and mole and Kelvin, and then we sort that equation, and you obtain the final one. And the part B is given to temperature, volume, and gauge pressure. We directly sorted it and calculate the mole numbers of total gas. Yes. total gas mixture. And total gas mixture contains some amount of carbon dioxide.
So decided that time the more fraction.
Yes. Yes. That law is only for carbon dioxide. General, salt solution inside the container. Inside the solution, the A is the solvent, C is the salt and solvent. After that, we are inserting another solvent container. The mass of another solvent is given. Then solvent A and solvent B are immiscible. And then after inserting the shaking, we observe two distinct phases. A plus C1 and B plus C2. Because the salt of C is dissolves in two solvents. And it's giving to us a relationship that while X, a fraction of the mass fraction of that phase is the mass fraction of belongs to that phase. And it's giving to us this here. This fraction. That's
Is that XC or what?
this is XC, this is YC. And we have the relationship YC is equal to which here is the question is asking us determine XC and YC and the mass of liquid X. Can I use this question? Because we already know that 20 grams of C inside the container. But A dissolves inside, sorry, C dissolves inside A and B. So some part of C goes this phase, some part of C goes another phase. But we know that the total C, C1 plus C2, is going to be 20, because it was at the beginning. But we don't know the exact amounts. Right? Is it clear? Oh, 200 grams, sorry. Oh, which is 200 grams. No, it's given up. First it says that we have 100 grams solvent A, 20 grams salt C. And then after that you have inserted another solvent. But it says that solvent A and B are immiscible. And we are checking that. Some C goes to part B, because you will observe the two phases, because they are immiscible with each other. But some amount of C goes in B part, some amount of C in A part. But we don't know the exact amount. We know the total mass of C. Which one?
Below that.
20 grams. Can I raise the question? Do all the work here there. And shake it, and then you will observe two distinct phases. Let's say M, there's a solution containing C plus, let's say, C2, because we don't know if they come out here. But you know the mass fraction of C, so values, C. The rest will be YB, but we can describe it in terms of YC. It's going to be 1 minus YC. The another phase, let's say P, P-gram solution contains A plus C1, and the mass fraction of C and mass fraction of A Let's do the real freedom analysis. What are the unknowns? Let's start from first. We don't know M, we don't know P. We don't know YX. If we know YX, we can find YB, so this is not unknown. If we know HC, we can find HA, so it's also not unknown. Only unknown is HC. alternate equation. So it will be 3 species mass balance. And one equilibrium relation. What is that? Question. Therefore, our degree of freedom 1 minus 4 is going to be 0, which means solid. If we write the overall mass balance for our equilibrium, we are inserting 100 gram A and 200 gram C and 500 gram B. This is the total mass that we are feeding the container. We know that we cannot create mass or we cannot destroy it. The total mass always conserves. And it's going to be equal to M plus P. M plus P is another constant. Can I use it? Let's do the species mass balance. It's going to be 50 gram that we are inserting. B is only here, so we don't need to take into account this part. It's going to be 1 minus yc because this is the fraction of B. The total mass is M. And then we already put this. And let's write the area mass balances. We are feeding 100 gram A to the system, and then you need to get, because there is no A here, we will just use that string, that phase. The fraction of A is here, 1 minus xc times total mass P. Next up, C is gases. We got 20 gram C, and some of them went to M phase. You know the fraction of it by C, and plus the another phase comes as fraction of C, and that phase. And also, we know that yc is equal to 2xc. So, 2xc plus so we eliminate the YC on that. You can also eliminate here. The C mass balance contains M and P. If we find M mass amount in terms of XC and P mass amount also in terms of XC, if I insert them to write down this equation, I will get an equation that contains only one atom. Let's say it. We can say that the M is going to be 50 over 1 minus 2x. And also here, we can say that P is 100 over 1 minus x. We can insert the P and M, the C mass balance equation, and that equation will contain only one atom. Can I use? Now C balance is now this final C balances. And then I will get quadratic equation. And then if the x is that fraction, by c equal to 2xc, and then 2 times 0.082 We know that M is 55 over 1 minus YC. Do you have any question about it? Can I move on to the next one? M is 60.49 gram. P is 109.49 gram. We calculated XC from that cartridge location. It was 0.0867. It's the mass fraction of C. And mass fraction of C in the lower parts, lower part phase. And upper part phase, you know the mass fraction relationship, YC is equal to 2AC. And we inserted here, we got the final, what we see, mass fraction of C. And then we already defined our P and M in terms of XC and YC. I just collected. The next question is from the book. Question number is 4.36. Everybody has the book, or do you want to read the question? Okay, I'm reading the question. In the production of the bean oil, bean contains 13 weight percent oil and 87 weight solids are grounded and packed to stored tank, along with recycled citrine liquid and phase. The PT ratio is 3 kg, 87 per kilogram means. The ground beans are suspended in the liquid, and essentially all of the oil in the beans is extracted in the head. The extractor effluent passes to a filter. The filter cake contains 75% mean solids and the balance oil, mean oil and hexane. The later two in the same ratio in which they emerge from the extractor. The filter cake is discarded and the liquid filtrate is fed to a heated evaporator in which the hexane is vaporized and oil remains as a liquid. The oil is stored in drums and shipped. The hexane vapor is subsequently cooled and condensed, and the liquid hexane is condensed is recycled to extractor. We are seeing the process in the picture. The part A is asking us draw and label flowchart of the process to the degree of freedom analysis and writing efficient order. The equations you would solve to determine all unknown system variables, solving the variables for which you would solve. That's the part A. You can take basis one under other means. Says that it's a recycled stream extracted out of the same place and stream of these are pretty good and we know the this is M1, our solar hexane. And we took our basis 100 kilogram. And the question says that the ratio is, the heat ratio is 3 kilogram, hexane per kilogram means. If the ratio is 3 and we took 100, that amount will be 300 kilogram hexane. And then we reference it on the extractor, let's say M2. We don't know mass fractions, solid, and mass fraction of oil, and also the mass fraction of hexane. After the filtration, we have filter cake. Let's say this is L3. We know the mass fraction of solid L3 is 0.75 kilogram per square kilogram. We don't know mass fraction of oil here. And hexane mass fraction will be 0.25 minus 1, 2. And then the upper stream goes to evaporator to obtain oil with our product. We don't know here that and mass fraction of oil or oil and mass fraction of everything. And let's consider that the evaporator evaporates the hexane, this is our solvent, this is the vapor, and goes into the condenser cool the vapor and condense, and we are feeding it back to our pressure. This is our cycle. Our unknowns. Let's examine our degree of freedom overall and for each unit. For overall, for just this part, I don't know, but you know that overall. There are two unknowns. Which are M1 and M5. Oh, sorry. We don't know M6, and also we don't know Y2. These are overlaps. We have 1, 2, 3 spaces, so we can have 3 spaces mass balances. Therefore, the overall degree of freedom is going to be 1. Well, in the filter case, this ratio will be the same as this ratio, right?
That is what it is. This E ratio is 8 kilogram hexane to kilogram.
Yeah. But in overall, we don't look at this one. For each part, for example, we will use for filter part.
So that E ratio for the
Yeah, it's going to be for the filter, right? We are looking at parts for the overall. When we look at the overall, let's go into the overall one. The recycle overall. So we will just look at the outside value. This is our outside stream and one. This is 100 kilogram small, so I don't write it. here, but you don't have 3. So you put it
So
here.
for the overall, you don't like the 1 for the third.
No, because this is all.
Well, you're right.
Because this is our cost. Yeah. Okay. Different for the site. Yeah. Oh yes, yes, this is right. And also, okay, let's say recycle is 5, that we don't know. Yes, sorry.
But, because of these ratios, 3 kilograms next day, kilogram B.
Yes.
So it basically says that 100, we're taking basis 100, right?
Yes, right.
So we can get in 1, right?
Right, the ratio is 3, right?
Yeah, so 3.
We are saying that our beans amount is 100 kilogram. So hexane amount will be 3 times 1. Yes, so that's going to be 300 kilogram hexane. I don't want to get...
And 1 B known then?
No, we don't know this amount. We know only after the mixing, after the recycle comes, it's mixing here, and then we only know the amount that we are feeding the extractor. Not that
I didn't see it, but
yeah, this is the recycle mixing point.
we're talking about.
No, this is only the hexane, right? And we know the amount, because the person is saying that the ratio will be 3. So if you take a basis 100 kilogram, that amount will be 300 kilogram of pure hexane. There is no other fraction. Because this is the vapor, comes from the operator, only the hexane. And then the cooler is condensed and goes back to here. At the mixing point. Is it clear right now? Yeah. I'm also creating some that was the ground things are suspension in the liquid, and essentially all of the oil in the things extracted in hexane. The extractor does filter. Filter kit contains 75% clean solid and balance over hexane, and relative to in the same ratio which they emerge from the extract. So it's the same ratio. Let's describe it also too. The ratio will be, it says that the same ratio, only let's write the ratio. That ratio will be equal to this ratio. And that will be 1 minus x2 minus y2 is going to be the ratio that here we will obtain. It's also given us. No, the question says that this ratio, the oil per hexane, is going to be same in the filtrate, the oil per hexane. So this is the relationship. It's already given
So you're
us.
looking at the filter system, right?
Not that, just right relationship, because it's given us. Just keep it inside. Then let me write degree of freedom for each unit.
Under three, it should be 75%. So, for the table, 75, 8%.
Here, right?
Yeah.
Yes, this is the 75 kilogram solid, right? The another will be, we don't know, that will be oil. The hexane will be 1 minus 0.75 minus Y3, right? Because they must be equal to 1. And it's going to be 0.25 minus Y3. Let's run we have we have we don't know M2. We don't know X2 and Y2. Because we know that how many kilograms we are feeding in terms of bean and hexane. Only the unknowns are here. If you know X, Y, and Y2, you will find out hexane mass fraction. We can have 3 species balances. This is because we have 3 species, oil, solid, and hexane. Therefore, for the extract, the degree of freedom will be 0. That's going to we don't know M2, we don't know X2, Y2, we don't know M4, we don't know Y4, we don't know M3, yes, Y3, yeah. 1, 2, 3, 4, 5, 7. So we have 7 elements. We have 2 species that we are feeding the filter. So we can write 3 species balances for that filter. And we have one relationship, yeah? It's going to be and we have also another point, this is the mixing, that fresh heat and cycle is mixed here, and then after that it's feeding the extractor. Let me write it also. At mixing point, we don't know M1, we don't know M5. So it's going to be 2 unknowns. This is the only one species, so we can write only one mass balance. And the degree of freedom is going to be 1. Do you have any suggestions to start with? No, 2 feeds. One feed contains only hexane, the other is contains bean.
So
these two things, Q2 and XA, and beans, they have the relation, and I want to be included in the
Right. For which operation unit?
for the overall.
For the overall.
Yeah.
For the overall one, we don't know M1, right?
Yeah. For the equations for the overall, you have the three speeches. And the relation between the speed for the speed and yeah, so that's four.
Right. You know that it took us, the weight is 100 kilograms, so it's small. Right?
Yeah.
It's smaller than all. We just decided that if we take that 100 kilogram, what's going on there? Yes.
But according to the problem,
Which class? Do you have any suggestion to start the question? Because we offered the analysis for each unit and overall, do you have any suggestion to start the question?
Sure.
Yes, because the video field is here, right? Let's do it. We are feeding 300 solvents and 78 solids. That's 13 oil. It's going to be if we know and do, and we can write spaces for space. That's all it is for the solids. Solids, balance. It's going to be 87 that we are feeding to exactly, which will be x2. The expression times we know the total amount 400. It's going to give us mass fraction of solids after gas action. It's going to be 0.175 kilogram solid per kilo. Okay, we can write it for the oil also. Kilograms oil. And it's going to be like 2 times times 2. And then times 2 is 400. And times 2 is going to be 0.0 kilogram oil per kilogram. Then we can move on for filter. We are filling the filter. Let's let the solvent solid mass fraction that can calculate with 0.175. It's going to be good. We know that the solid is only here. The question says that this the fraction is 0.75 for solid here. And it's going to be 0.75 times M3 because there is no solid. Okay. Then M3 is going to be 116 kilo. If you know M3 and M2, you can do overall balances to find M4. We also know about ratio this ratio and here 3 and 0.3 fractions, 3 minus 3. This ratio and this ratio must be good because the questions says that we calculated y2 and x2, so we can start that ratio. No, so y2 is going to be 0.0. After knowing the y3, you can use it for oil bonds for the filter. Yes. Yeah, this is a bit going to be density contains zero and density contains zero. Did you sign that? And 1,4 is going to be 0.04. If you know y4 and m4, you can calculate M5. That's because the hexagon only goes at density that contains only O. to know the M5, we can calculate the M1, because we know the amount that we are getting extracted, and we calculated M1, M5. We have to always balance here at the mixing point. The only unknown that we don't know M6. And we generate evaporated oil balance because only oil will go here. There is no oil at recycle stream, in the recycle stream. Do you have any questions? Is it clear or other complex? Yeah, there are also calculations important because we have to know which point you will start and after finding written information you will insert another one and step by step you will calculate it. I hope it's going to be helpful for you in the exam. Thank you for coming.
Thank you. Thanks. That's good.